Okay, so we're into section 1.4, and we're going to probably do problems 7 through 12. And yeah, I guess we'll do 7 through 12, but we'll do them one at a time. So what it says find the limit if it exists. If it does not exist, explain why. So what we have are what are called one-sided limits. And so in this case, we have something that kind of looks familiar. And when x equals 5, this goes to 0, and x equals 5, that goes to 0. So if you just plug 5 in, then you're going to get an indeterminate result. Now, what it means here is, what is the limit when you come from the negative side, so from 4 towards 5. And when you have actually, when the limit exists, the one-sided limits are the same as the limit. The only time this is not true is if you have something like a vertical asymptote, or you have some kind of piecewise function that's defined, from A to B it's this function, from B to C it's this function, etc. So because this is indeterminate, we can just treat it as a normal limit. So this one-sided limit, what we could say is, let's call this f of x is this function that we're looking at. And so what we could say is that the limit as x approaches 5 from the negative side of f of x equals the limit as x approaches 5 from the positive side of f of x is equal to the limit as x approaches 5 of f of x. And if this is true, if the limit is the same coming from the left-hand side or the right-hand side of the number, then this is true. If they're not the same, then the limit does not exist. So all we have to do in this case is just do the normal thing that we've done. And because we're getting, we have polynomials here, we can factor the expression. So the numerator stays the same for right now. We factor the denominator as such, and we use canceling out. So then we get, we're taking the limit as x approaches 5 from the negative side of 1 over x plus 4, and then we just stick 5 in. So the answer is 1/10. Number 8. So we have the limit as x approaches to the positive side of the quantity 2 minus x over x squared minus 4. So again, if you plug 2 in, just the number 2, you'll get 2 minus 2, which is 0, and 4 minus 4, which is 0, so it's indeterminate. So the same as last time, we can just do this as a limit. Since we don't have a vertical asymptote, we have an indeterminate result. We can just figure out what the limit is going to 2, and everything's fine. So we're going to use factoring out again, and I'm going to rewrite the numerator as x minus 2, the negative of x minus 2, and then you can factor the denominator as x minus 2 times x plus 2. So then we can cancel this out, and if you let x go to 2, then the result is going to be negative from here. We have 1. We cancel this out, we didn't get 0, we got 1. And then you divide by x plus 2, which is going to let x equal 2. And so the answer is negative 1/4. And the same would be true, that the limit as x approaches 2 from the negative side of this function, same function, is also negative 1/4. And we can also say that the limit as x approaches 2 of f of x is also negative 1/4, because these two are true. So since the limit is the same coming from both sides, then the limit exists. Okay, we're on problem number 9. The limit as x approaches 3 from the negative side of x over the square root of x squared. Okay, so this one's different because if we just plug 3 into there, you would get 3 divided by 0, because you'd have 3 squared minus 9 is 9 minus 9 is 0. So this is now infinite. So what does that mean? Therefore, we have a vertical asymptote at x equals 3. So the question is, do we, when you come from the left-hand side, is it going up to infinity or is it going down to negative infinity? So the way you can do that is you pick a number close to negative 3 and see what happens. Does it go negative or does it go positive? That's all you really care about. You know it's going to infinity, so we really don't care what the number is. We just want to find the sign. So what we'll do is, let's say, let x equal 2.9, which is less than 3. So this is coming from the lesser side. That's what that means, not negative 3, but from the smaller side. So you could just plug the number in and answer it. There's a couple of ways of doing it. So if you just plugged it in, you'd have 2.9 divided by 2.9 squared minus 9. Take the square root of the whole thing in the denominator. And you can plug the numbers in. But really, you just want to think of it in terms of what is happening here. And actually, just realize something. Oh, it's negative 3. Okay. I was thinking, what? Is that true? Yeah, because otherwise the function does not exist. Okay, so, So let's, so it's negative 3 to the negative side. So let me go back here. So here's negative 3, so actually we want negative 3.1. So let's go fix that. So if you just plug in negative 3.1, you get negative 3.1 divided by the square root of negative 3.1 squared minus 9. Okay, again, you could plug it in, get a number. It would either be positive or negative, but we can kind of look at it just from a sign standpoint. So the numerator is going to be negative. The denominator, well, it has to be positive because you're going to take the square root of a number, which to take the square root has to be positive. But if you square 3.9, so what we can say is that negative 3.1 squared is going to be greater than 9. When you square it, the negatives cancel out. And 3 squared is 9, so 3.1 squared has got to be greater than 9. So this is true. So if that is greater than that, then you're going to have a positive number here. And then you take the square root, which is a positive number. So now you just look at the signs, and if you had negative divided by negative, it would be positive. If you had positive divided by positive, it would be positive. But if the signs are different, then you're going to have negative. Whether this is negative and this is positive, or this is positive and this is negative. So the answer is going to be negative. And because of that, what we can do is we can say two things. You can say that let's see, the limit as x approaches negative 3 from the negative side of x divided by the square root of x squared minus 9. You could say it does not exist, which is true, but in these cases we actually say it's going to be, it's approaching negative infinity, so it gives us an idea of whether it's going up or going down. Okay, number 10. So we're going to, first thing we're going to do is just plug in the number. In this case, positive 4. We're going to look at the limit going from the negative side, so 3.9, 3.99, etc. So what happens? Well, plug 4 and you get square root of 4 minus 2. Square root of 4 is 2, so you get 0. And you get 4 minus 4 is 0. So it's indeterminate. So again, what we have to do is just evaluate the limit as x approaches 4, and that'll be the same on both sides. Because we have a radical square root sign, then we're going to use rationalization. So let's just take the expression, put it in parentheses, do the same thing in the denominator, multiplied by the square root of x plus 2, divided by the square root of x plus 2, multiply out the numerator and you get x minus 4. In the denominator you get x minus 4, surprise, surprise. Then times this thing, cancels out. So the limit of this is the same as the limit of 1 over the square root of x plus 2. And we just plug in 4. So that's going to be equal to 1 divided by 2 plus 2, which is 1/4. We can also say that the limit as x approaches 4 on the positive side of 1 over the square root of x plus 2 is also equal to 1/4. And we can say that the limit as x approaches just 4 of this thing, which is the same as the original thing, so is also 1/4. I should have actually put that in there. Okay, we're at number 11, which is a little tricky. So I have the absolute value of x divided by x. So this is one of these absolute value things. And when you put 0 divided by 0, you get something that's you get indeterminate. Right? But that doesn't necessarily mean that the limit exists. So anytime you have this absolute value thing, you don't worry about that. So what you can see is when x is less than 1, the absolute value of x divided by x is -1, because this will be positive all the time. This will be negative when x is negative. When x is less than 0. When x is greater than 0, the absolute value of x over x is equal to 1. So if we were to plot this function, it would look something like this. We come along, we get to 0, the function would not exist at 0 because it's indeterminate. But in this case, the limit is different depending upon which side you come from. So the limit as you approach from the positive side is +1, and the limit as you approach from the negative side is -1. So the answer is equal to 1. And if you do the other one, which is what is the limit as x approaches 0 from the negative side of the absolute value of x divided by x, it's going to equal -1. And since this limit does not equal, where I wrote it down here, this limit, since the limits are not the same, so since the limit as x approaches 0 from the positive side of this function does not equal the limit as x approaches 0 from the other side, the limit as x approaches just 0 of the function does not exist. And it's not like a vertical asymptote where it approaches something, it just does not exist there. Function does not exist, the limit does not exist. Okay, this is problems 33 through 40. And what we're asked to do is determine if there are any values where it is not continuous. And if there is a discontinuity, is the discontinuity removable? So 33 is a polynomial. And all polynomials are continuous. So just from that fact, it is continuous. Okay, so 34 is f of x equals 1 over x squared plus 1. So this is a rational function, so it has a possibility of being discontinuous. The only place this can be discontinuous, well, there's two places it could be discontinuous: at a case where you have a common factor, but the numerator is not it's just a constant, so that's not going to happen. And the second case is if the denominator can go to 0. Well, because x squared is always positive, the denominator is always going to be positive. It's never going to be 0. So, so this one is also continuous. And it's basically because the denominator is always positive. Okay, 35. So if you have a continuous function and you add or subtract another continuous function, the resulting function is continuous. So this part of the expression is continuous because it's a polynomial. This part is continuous because both the sine and the cosine are continuous. The other trig functions have discontinuities. So this composite function is also continuous. 36 is also the cosine function. The only difference is it has a pi over 2 coefficient in front of the x inside the argument. So this is also continuous again because the sine function and the cosine function are always continuous. They just go up and down, up and down, up and down between 0 and 1. Okay, we finally have one here that is discontinuous. So here we have x over x squared minus x. So we could have a discontinuity due to a common factor, or we could have a discontinuity due to the denominator going to 0. So what you have to do is you have to factor. So we can actually factor out an x in the denominator. So you see we do have a common factor. So at x equals 0, it's discontinuous due to the fact the function is undefined. Because you have 0 or indeterminate. You get 0 over 0, which is indeterminate, so the function does not exist at x equals 0. It is a removable discontinuity because these kinds, the indeterminate form of a discontinuity can be removable. So what we do is we would take this kind of simplified version, which is you cancel out the x's, which would be 1 over x minus 1, and you evaluate that at x equals 0. So we could say evaluate x minus 1 at x equals 0 because that's the point of discontinuity. So if we plug in 0, we'll get 1 over x, or 0 minus 1, which is negative 1. So how we would do this, how we remove the discontinuity, is we would say for x between negative and positive infinity, f of x equals x over x squared minus 1. For all this except x equals 0. At x equals 0, f of x equals 1. So this, without this, this function, without this additional comment, has a discontinuity. But by putting in a value of the function which is equal to the limit of this function as x approaches 0, that removes the discontinuity. So that's the first discontinuity. The second discontinuity is at x equals 1. We are also discontinuous. And that's because we have a vertical asymptote. Now, asymptotes are non-removable, so we can't do anything about that. Because what will happen is this at x equals 1 will go to positive infinity and come from negative infinity. Okay, 38. So the function is x over x squared minus 1. So it's like the previous problem. We want to see whether we have a common factor, which we don't in this case, because if I factor the denominator, I get x minus 1 times quantity x plus 1. So the inside, the inner and outer terms cancel out. So x times x is x squared, and negative 1 times positive 1 is negative 1. So that's factored out. You see that this is not either one of those. So there is no common factor. So we have two discontinuities. One at x equals positive 1, and one at x equals negative 1. That's where the denominator will go to 0, and the numerator is non-zero. And they are non-removable because they are vertical asymptotes. So there are two kinds of non-removable, well, it's three. We talk about two of them, vertical asymptotes, and if you have that absolute value function that jumps up, that's another case. Step function is also an example of a discontinuity that's non-removable. Okay, so we have another rational function. Instead of minus 1, we have plus 1 in the denominator. In this case, the denominator, we can't factor this and get real results. So this is as far as we can go. And because you can't factor this, and also because this term is always positive, there are, this is continuous for all real numbers. The function actually looks something like this, I think. If you plotted it out. So since it's not discontinuous, since it's continuous, we don't have to talk about discontinuities. And I think 40 is the last one. So in this case, we have x minus 3 over x squared minus 9. So the two possibilities that we're going to look at are a common factor. So to be able to find out what is a common factor, you have to factor the denominator. So there's this common factor. So we can say 1 discontinuity at x equals 3. That's this one. And because it's a because it's a discontinuity not due to going to infinity, but because we get an indeterminate result, what we're going to do is we're going to evaluate the reduced form. So we cancel, have the common factor we cancel out, and we're going to evaluate that at the value of the discontinuity, the x value. So that'll give you 1 over 3 plus 3. The x is 3. 3 is a constant, so you get 1/6. So just like before, to remove this discontinuity, so it is removable, and again, so you could say something another way if we're doing it for all x except x equals 3, f of of x is the original function, which is x minus 3 over x squared minus 9 at x equals 3, f of x is equal to 1/6. And that value bridges this hole that's in the function, where we have a indeterminate result. And then we also have one discontinuity at x equals -3, and that makes this go to 0. But these are non-zero. You'll have -3 minus 3, which is -6, and we have the same thing here, so this cancels out, and you get 1 over that. And so we have a discontinuity here. It is a vertical asymptote. Therefore, it is non-removable. And that's it. Okay, this is problem 48. And this is one of the few examples that I do that have a piecewise function. You can make these limit questions hard than you need it to really be. So for some of you guys, you might like the extra challenge, but some people just get frustrated. So anyway, this is a little. So what we're looking at here is there's two functions that are joined somehow or another. We don't know exactly what they're like, but they're both polynomials. So what you could do is, okay, this is great. This is x for greater than 2. So at 2, x equals 2, there's two functions, and if the limit exists, so what are they asking for? I've already forgotten here. Find the values, if any, at which f is not continuous. Which of the discontinuities are removable? Okay, well, each one of these by themselves is continuous because they're polynomials. The question is it continuous at x equals 2? And so let's just do that. Let's see what f of 2 is for the first part of the equation. So you'd have -2 times 2 is equal to -4. And then you look at f of 2 using the second equation. And I know it doesn't say equal to, but if it's equal to, if we said equal to 2, and this value comes out the same as the value, then we know it's continuous. It may not be smooth, but it is continuous. Okay, so we have 2 squared minus 4 times 2 plus 1. That doesn't look like it's going to work out. So you have 4 minus 8 is -4 plus 1 is -3. So we can see that it's going to be discontinuous, and it's not going to be removable because we have a jump. The only time you can have a removable discontinuity is when the function does not exist because it's indeterminate. As far as this is concerned, the function exists at x equals 2 because this part of the function applies. So let's switch here to okay. It says I'm sharing my entire desktop, which I didn't realize I was doing. But that's okay. I do not have anything to hide. I don't think I do, at least. Oh, I know what it is. It's not sharing my entire desktop. I just need to stop sharing, and then I can share my entire desktop. There we go. Okay, so let me get rid of that. So here's my graphing program, which I've downloaded, so I can have it read available. Unfortunately, government school students can't download it because they've got those things freezed. So here's the graphing program. So what we're going to do is I'm going to plot both of these functions separately, and then we'll use the domain restriction. So we have negative 2x and we have x squared minus 4x plus 1. Graph. Push the graph button. Okay, so what it says is for x less than 2, we're the red curve. And for x greater than 2, we're the blue curve. So we go from here, jump up to there, and then it's the blue curve. So there's no way that we could put a point in here and get it to be continuous. You need a whole bunch of points that would draw a vertical line there. Maybe that would be one way of doing it. If I went back here instead of 4x plus 1, if I just had 4x and graph that, then you could see it would be continuous because the red curve would be in play for x less than 2, and the blue curve would be in play for x greater than 2, and then at x equals 2, they're both the same thing. So that would be a continuous function. Piecewise continuous function is what they call it. So the answer to the question is are there discontinuities? Yes. Is it discontinuous? Yes. Can you remove it? Remove. No. It's not a vertical asymptote, but it's a jump in the thing. Okay, so we're doing problem 57. And let's read the instructions again. Find the constant a or the constants a and b such that the function is continuous on the entire real line. So if you watched the last problem, 48, you saw how I changed the second equation from x squared minus 4x plus 1 to x squared minus 4x. And at that point, the two curves were continuous, with plus 1 added. They were not continuous. So we just have to choose the values of x so that happens. So the function f of x consists of two parts. We have the domain when it's less than 2. So when x cubed, it's f of x equals x cubed when x is less than or equal to 2, and it's equal to ax squared when x is greater than 2. So it's continuous everywhere except possibly at x equals 2, depending upon the value of a. So let's just say a is 1. What would happen? So if you did f a equals 1, f of x cubed, we'll say that, would be 1 cubed, or actually a equals 1, so you're plugging in 2. So let's say f of 2. F of 2 using this would be 2 cubed, which would be 8. But if you use the second equation, f of 2 would be 1, because I just said a is 1 just for illustrative purposes. You'd have 2 squared, which is 4. So since 4 does not equal 8, it's discontinuous. So you can hopefully see what we have to do to choose a correctly is we have to have this happen. So what we would do is we would say 2 cubed has to equal a times 2 squared. So that's this function, first thing on the left-hand side, and the second one is ax squared. And if I choose a, I picked a equal to 1, and they didn't equal each other. So the question is, what is a for them to be equal? You just solve for a. So is 2 cubed over 2 squared. 2 cubed divided by 2 squared, which is 2. Therefore, a equals 2. So if we specifically said this is our function and we're going to let a equal 2, and so it's 2x squared for x greater than 2. If we now plug in 2, we'll get 2 cubed is equal to 2, that's this 2 here, times 2 squared, and so 8 equals 8, check, it works out. And so I'm going to go to the graphing program and just show you what happens. So let me stop sharing here. So that was what was on last time. So we're going to put x cubed and x squared. So this is where a equals 1 case. And you can see at x equals 2, they don't match up. Whereas if we go back here and change the second equation to 2x squared, and that's not quantity 2x squared. If I did that, I'd have parentheses around it, but it's 2 times the quantity x squared. Okay, then you graph it. And if we zoom out, you can see here at x equals 2 that the functions are equal to each other. So for x less than 2, we're following the red curve. And then when we get to 2, we follow the blue curve. So that's what that graph represents, blue and then red. We kind of ignore this part. And the blue part here is not, and we ignore the red part, this red part here.